Good evening, everyone. A warm welcome to all the participants to the fourth day of our faculty development program. We are delighted to continue this enriching journey of learning and knowledge sharing with yet another insightful session. Over the past 3 days, we have gained valuable knowledge and perspectives from eminent experts, and we look forward to another engaging session today. It gives me great pleasure to introduce our esteemed resource person for this session, Dr. Vinod C., Professor and Head of the Department of Electronics and Communication Engineering at Sripadi Institute of Management and Technology. With more than 17 years of teaching and research experience, he has established himself as a distinguished academician, researcher, and mentor. He obtained his PhD in Electronics and Communication Engineering from Nurul Islam Center for Higher Education and his Master of Engineering from Anna University. His research interests span diverse and emerging areas, including machine learning, deep learning, biomedical image processing, and artificial intelligence. Throughout his academic career, he has been actively engaged in research, innovation, and the guidance of students and scholars in cutting edge technologies. He has authored and co authored numerous research papers in reputed international journals and has presented his work at several international conferences. He is a life member of the Indian Society for Technical Education, a member of the International Association of Engineers, and serves as a reviewer for international journals and IEEE conferences. Today, he'll be delivering a session on renewable energy, energy harvesting, and self-powered wearable systems. We are delighted to have him with us and eagerly look forward to gaining valuable insights from his expertise and experience. Sir, we are honored by your presence and kindly invite you to deliver your session.
Yes. Uh, Thank you. Thank you, Anashara, for your warm welcome. Am I audible?
Yes, sir.
And I think my screen is visible to all of you.
Yes, sir, visible.
Let's start with I'm very glad to have to present a session before you all on the topic um, renewable energy, energy harvesting, and powered wearable self-powered wearable systems, smart biomedical, sustainable electronic systems for AI, IoT, and green technologies. So, starting with uh, a very good evening, everyone. Welcome to the session. And today I will be presenting a topic on renewable energy, energy harvesting, and the wearable systems. Uh, with the rapid growth of the wearable healthcare devices such as smartwatches, ECG patches, health sensors, etc., there is an increasing demand for sustainable and energy efficient power solutions. Traditional batteries have limitations, including limited lifetime, frequent charging, and environmental concerns. That are the major issues that we are facing currently. We need even our mobile phone laptops needs frequent charging and limited lifetime issues and environmental. Energy harvesting technologies it's provide an attractive alternative by converting ambient energy sources such as sunlight, body heat, etc., into electrical power. So combined with AI and IoT technologies, these systems enable intelligent, autonomous, and sustainable healthcare monitoring. So in this presentation, um, we'll be discussing about the various energy harvesting techniques, then self-powered wearable architectures, then research developments in this particular area, energy harvesting, etc., and future opportunities. So moving on to the topics, and today we'll be dealing with the main areas will be renewable energy in healthcare systems, energy harvesting techniques, then self-powered wearable systems, then integration of AI and IoT to this healthcare environment, then challenges and future trends. After that, I will be discussing about various recent research trends through which we have to the problems and solutions of this particular era, and then into the conclusion. Okay, moving on to the first slide. As an introduction, I have to say the biomedical electronic systems, they are transforming modern healthcare by enabling continuous monitoring, early diagnosis, then personalized treatments, etc. The examples include the ECG monitors, glucose sensors, smartwatches, some wearable medical devices like this. Then, however, as a number of connected healthcare devices increase, the energy consumption dependency also increases. This is one of the major issue here. The healthcare devices, as the values or the outputs are increasing, the energy consumption and battery dependency is very high. Even if we are using mobile phones and all, we have to maintain a healthy battery and maintain proper charging um, to maintain the connectivity and all. Similarly, the healthcare devices also, they are in need of sufficient power and sufficient battery life for their continuous or uninterrupted operations. So sustainable biomedical electronic systems aim to address these challenges by incorporating energy efficient hardware, then renewable energy sources, intelligent power management, and environmentally friendly materials. So as I said, we are discussing about the smart healthcare technologies, then wearable devices, then sustainable electronics, then green healthcare initiatives. So what do you mean by healthcare sustainability challenges? For the challenges that having uh, the sustainable development of healthcare environments. So, major concerns are the growing demand of wearable medical devices that we have to incorporate many type of sensors to human body to measure or sense different parameters of the body. Then frequent battery replacement issues. Main issue is the lifetime of the battery. The power source is getting degenerated very soon, and the electronic waste generation, e-waste. It's one of the major issues of the e-waste. It's not due to healthcare e-waste. A lot of sources of waste is we have to deal with, and need for sustainable healthcare solutions. So we are more into solutions, not only sustainable solutions we are seeking. So now we are talking about self-powered wearable electronics. That means self-powered, the term self-powered means in order to have a continuous health monitoring systems, we need systems that are self-powered. That means the power is to be maintained or means purely dependent on battery environments are to be eliminated or are to be replaced with a continuous health monitoring systems. So reduce maintenance and longer operational lifetime and environmental friendly. These are the major points that we have to consider while developing such self-powered wearable devices. In the case of healthcare technologies, uh, we are moving into, or we are moving towards the green technologies that are supporting this growth or development. Most healthcare electronics depends on batteries, which requires periodic replacement, and it contributes the electronic waste. Then millions of batteries started every year. We are all aware that millions of batteries at button type cells and all, they are just disposed some areas or discarded some areas, and it's not environmental friendly in nature. And the green technologies focus on reducing environmental impact through renewable energy, recyclable materials, and low power electronics. So we are trying to integrate green technologies into biomedical systems so that we can improve the device sustainability while supporting global environmental goals. Uh, so to have a smart healthcare and system which is having sensors, communication technologies, AI, and data analysis to provide advanced healthcare services, wearable electronics play a crucial role in this ecosystem. That means that we are all having means devices like smartwatches, fitness bands, ECG patches, then smart tech states, etc. These are all, we are going to discuss these things in the coming slides. These devices continuously monitor physiological parameters such as our heart rate, blood oxygen level, then temperature, then physical activity, etc. The controlled in a controlled environment, the data collected can be analyzed using AI algorithms and transmitted through IoT networks to remove to a particular means or remote healthcare monitoring environment. As wearable devices become more common, deploying sustainable power solutions become increasingly important. So here, energy is the main. It is an important parameter. So we need energy, and we have to harvest energy. So we are more into energy harvesting techniques. So what are the sources of energy? So you all know the sources of energy. It's we are aware of the source of energy like light, heat, motion, radio frequency signals, biochemical reactions, etc. So the renewable energy means the energy obtained from naturally replenishing sources for wearable biomedical devices. Several sources can be utilized as the flexible photovoltaic cells that can be integrated into clothing. Then thermal energy, mechanical energy can be harvested from walking, running, etc. And radio frequency energy can be captured from wireless communication signals. Then biochemical energy can be generated from body sweat and glucose-based biofuel cells. Similarly, these sources offer significant potential for powering wearable healthcare systems. So I mean, seeking various sources that can be that is generating energy from our body cells, body heat, now our operations like walking, movement, etc. So the benefits of energy harvesting includes the self-sustained operation of these wearable devices. That means, despite significant technological advance, wearable healthcare devices still face several energy-related issues. Then, first change is limited battery life. That means many wearable devices require frequent charging. Then, miniaturization creates additional constraints because smaller devices have less space available for batteries. Similarly, continuous sensing, wireless communication, and AI processing further increases the power consumption. So we need to have a self-sustaining operation of the particular devices. Then we have to reduce the dependence on battery, and we have to increase the lifetime of the we need longer lifetime of the particular device. So these challenges motivate the development of self-powered wearable systems to harvest energy from the environment. So instead of relying entirely on batteries, the wearable devices can generate power from sources like sunlight, body heat, motion, vibrations, etc. The harvested energy can either directly power the device or it can be stored in the batteries, supercapacitors, etc. So we have already seen this slide. You are all aware that the solar cells we are using technology, solar cell technology for collecting light means solar energy. Then thermoelectric generators, heat signals or heat is collected to generate energy. Then for motion, we are using piezoelectric devices. So stress or strains can be converted into energy with the help of piezoelectric devices. And it's friction, that is triboelectric nano generators. That's not that much common word as solar and thermoelectric. Triboelectric is not that much common, but many of you are aware of the triboelectric nano generators. Then similarly, we are having piezoelectric nano generators also there. So we are about to discuss these different energy harvesting techniques. So first two or three, you are all very much familiar with. So before going into the energy harvesting or energy generation systems, we are just going to the wearable system architecture. So this is simple architecture where we are on the left hand side, we can see a user. The user will be wearing the wearable device, and the wearable device is powered with the battery. That's the particular battery or the wearable device is powered by some type of energy or cells that are powered by stored charges. Otherwise, they can be charged by signals or temperature or some motions of the human body. So these sensors are continuously powered or they are continuously activated by the energy signals. So these wearable devices will be collecting different parameters of the body like temperature, pressure variations, heartbeat like that. And they will be transferring those into wirelessly. Usually or most commonly, we will be having a mobile phone through Bluetooth connectivity. It will be transferred to the smartphone, and through wireless technologies like 4G or Wi-Fi technologies, it will be transferred to the cloud or internet. And from the cloud, means through different UIs, user interfaces, it can be accessed by healthcare professionals or research immediate family members like that. So this is a simple architecture of a wearable system where we are majorly concentrated on the wearable devices that is worn by the particular person. We are more into that wearable devices, wearable sensors, and energy consumption and power generation of that particular wearable devices. So these are all the different energy harvesting techniques. First one is solar energy. As you all know, it is having a flexible photovoltaic cells. And the solar energy harvesting is one of the most mature and widely used energy harvesting techniques. And the flexible photovoltaic cells that can be and the wearable accessories. This is somewhat it's available in our market. That is flexible smart watches are available. Flexible cells are used in backpacks, etc. Then these cells convert sunlight into electrical energy with relatively high efficiency compared to other harvesting methods. Then recent advances in a flexible and lightweight solar materials have made them somewhat suitable when we are combining it with other energy harvesting techniques like hybrid powered systems. So, yeah, means there is nothing much. Solar energy harvesting is one of the most common and cheap energy harvesting techniques. Then next one is thermoelectric electric energy harvesting, thermoelectric effect, Seebeck effect. Thermoelectric generators, Seebeck effects we have already seen. The thermoelectric energy harvesting utilizes the temperature difference between the human body and the surrounding environment to generate electricity. So this technology operates based on the Seebeck effect, where voltage is produced when two sides of a thermoelectric material are maintained at different temperatures. So you can see in the figure, it's just an animated representation where one side is comparatively uh, high in temperature and other side is cooler. Shows the representation of that Seebeck effect. Since the human body continuously generates heat, the thermoelectric generators, commonly known as TEG, thermoelectric generators, TEGs, that can convert this thermal energy into electrical energy. So thermoelectric energy harvesting is one of the energy harvesting technology. And the application of this include smart wristbands, health monitoring devices, wearable medical sensors, etc. Then the major advantage is continuous energy generation without requiring body movement. That means that usually the human body will be having a certain amount of temperature, and there will be a temperature difference between the natural, say, environmental temperature and the human body. Usually it will be means hot in nature. So, however, the power output is relatively low because the temperature difference between the skin and environment is usually small. So the recent research focuses on flexible thermoelectric materials that can conform the human body while improving energy conservation efficiency. So in each area, we are having different types of researches are going on to improve efficiency and suitability of the technology. So here also we are having a lot of researches. They are trying to improve the efficiency so that the power output can be increased sufficiently. Then another one, you are aware with the piezoelectric effect. So here we are having a piezoelectric crystal where the crystal is getting pressed or it will get some strains or stress through different moments like human running, walking, breathing, heartbeat, etc. The piezoelectric crystals get um, some stress or pressure, then it will be generating some voltage. Here, the piezoelectric crystals are certain materials such as piezoelectric ceramics, polymers, general electric charges generate electric charges when compressed, bent, or stretched. So we can keep these crystals where we can have some compression or bending or stretching happens. So while walking, running, breathing, and heartbeat, the beating of the heart, there will be some compression, bending, or stretching is happening. So in the case of wearable healthcare systems, energy can be harvested from everyday human activities such as walking, running, etc. For example, piezoelectric materials embedded in the shoe. We can embed that particular material in the shoe, and it can generate electricity during walking. Then the technology is attractive because the human motion is continuously available throughout the daily activities. So the power generation depends on the intensity and frequency of the movement. The researchers are developing flexible piezoelectric materials to improve and the efficiency of the wearable applications. Another one uh, is one piezoelectric energy harvesting. The process it can be termed as PENG. It's in some papers and all, it's denoted as PENG. It is piezoelectric energy harvester or piezoelectric nano generator. And PENG, piezoelectric nano generator. You can see that yellow thing, and it's acting as a piezoelectric nano generator. And we are applying an external force. And it is a device that converts mechanical energy such as vibrations, pressures, as I have already told, into usable electrical energy. When a material is compressed, internal dipoles shift, creating an electric potential across the material. As the piezoelectric effect as a piezoelectric material works, this is the same principle behind the piezoelectric nano generators also. Then next one, this is not that much means common, this triboelectric nanogenerators, TENGs. So here also the triboelectric nanogenerators are among the most promising technologies for self-powered wearable electronics. They generate electricity through the a combination of contact electrification and electrostatic induction. You can see it in the figure. When two different materials repeatedly come into contact and separate, electrons transfer between the surfaces, creating electrical charges. That means human activities such as walking, finger movement, clothing friction, etc., can be used for generate electricity. This TENGs offer several advantages, including lightweight construction, flexibility, low manufacturing cost, and high voltage. Because of these characteristics, tanks are widely used in smart textiles, wearable sensors, and electronic skin. And these are not not commercialized yet, but the research is going on to provide the triboelectric nano generators in our day-to-day life. Like this one, the mechanism is based on the spontaneous generation of electrostatic charge when two chemically different materials come into contact. Here we can see here tribo negative and tribo positive layers. So when they are pressed, during the pressing, some induction is happened and tribo positive and negative layers are generated while releasing. So this way, some potential difference due to the separation of the two materials, some potential differences, some induced electrical current in an external circuit, which can be used for powering the appliances. So this is one of the promising technologies and one of the major research areas where these tribo electric nano generators are having. And these TNGs usually they produce sustainable energy and they are having some positive thing, but the TNG themselves are generally not made from sustainable. That means these are made from non-sustainable elements or not made from renewable materials. So current one of another research area is they are trying to develop sustainable TNGs constructed from renewable or abundant materials resources. That means some renewable algae, cellulose, biomass, and clay. These are all the materials, or some other materials also. These are all materials they are trying to develop this triboelectric nanogen. That the materials is renewable in nature, and the energy is also sustainable. So it will be 100% efficient one. So we are using biopolymers, cellulose, etc. for clay minerals and other materials for generating this triboelectric nano generators. Then means using only the triboelectric nano generators is not a efficient or not a perfect solution for this energy harvesting. So we have to consider different types of tanks, that is hybrid TNGs and porous TNGs. In the case of hybrid TNG, the classical TNGs convert one mechanical energy source into electricity. That may be the periodic motion, wind, wave, sound, etc. But now the types of nano generators and cells can be combined in one hybrid nano generator. So one hybrid nano generator is the energy source will be of different types of sources. It can be termed as hybrid tanks, hybrid triboelectric nano generators. Another type is porous tanks. Porous means the particular surface of that particular material that having pores, and having pores that means the surface area of that particular charge buildup area, surface area will be high, so that this leads to more electrostatic charge and in turn to higher electric currents provided by the tank. So, in the case of porous tank, the surface area is increased with the help of porous structure so that it can provide higher electrical currents to the output. That is the difference between hybrid tanks and porous tanks. Now, this shows the diagram shows the PENGs. PENGs means we have already discussed about piezoelectric nano generators and TENGs. That means triboelectric nano generators. In the case of piezoelectric mechanism, you can see in the figure A, it shows a polling. Term polling. Polling means we are giving a particular amount of external electric field to align the piezoelectric material, internal electric dipoles. So after polling, the materials are properly aligned, and after the pressing operation and releasing, it will be generating some amount of voltage. That means these specialized materials with centrosymmetric crystal structures, they during this piezoelectric mechanism, they will be generating some amount of voltage. And it is represented in the form of voltage, which is proportional to the electric coefficient, then the force applied between the layers. But in the case of triboelectric mechanism, it's mainly due to the friction. You can say it's a friction, that is, tanks convert mechanical energy into electrical using contact electrification. That means it uses at least two materials with the different electron affinities. As the materials move closer or further apart, it induces a potential difference, pushing electrons through a circuit. Okay, this is the difference between pens and tanks. These two are having a lot of research works are going on in this piezoelectric mechanism and triboelectric mechanism, and the performance improvement of these pens and tanks is one of the major area where researchers are working to generate or develop sustainable healthcare devices and sensors. Next one is RF energy harvesting. We are all aware that the harvesting ambient electromagnetic energy. That means RF energy harvesting captures electromagnetic energy that exists in the environment. That common sources like Wi-Fi, cellular, Bluetooth devices, television broadcasts, and communication towers. These special antennas called, we can say or call it as rectennas. Rectennas means they are receiving RF energy. Rectennas receive these signals and convert them into usable DC electrical power. One major advantage is that RF energy can be harvested continuously without requiring the sunlight, heat, or motion. However, the availability and power density is relatively low, which limits its use in ultra low power electronics. RF harvesting is often combined with other energy harvesting techniques so that the efficiency can be support various wearable devices. Then another one, biochemical energy harvesting. Here also there are a lot of researches are going on. Here the biological substances present in the human body to generate electricity. In one way or other, we are to generate electricity from renewable or from in an efficient manner. So here in human body, glucose-based biofuel cells and sweat-powered energy harvesting systems. From human body sweat, and we can generate energy. So the principle is similar to how the human body produces energy through biochemical reactions. Human body reactions means chemical reactions that are occurring in the human body. Similarly, we are trying to generate energy. For instance, enzymes can convert glucose to lactate or lactate to present in sweat into electrical energy. So similar biochemical reactions that are happening in our body, we are replicating that one in order to generate energy. These technologies are especially attractive for wearable healthcare applications because they are naturally available body fluids. They are all naturally available. We are not in need of creating some other fluids and all. The electrolyte is readily available in the human body itself. Although still in the research stage, biochemical energy harvesting offers existing possibilities for powering implantable devices, biosensors, and long-term monitoring systems. So, coming into the next slide, why flexible and stretchable electrons? In every aspect, we are wearing sensors or we are wearing the devices and we are wearing the health monitoring setups. So, wearing something, it produces some discomfort. But in the case of in order to provide some comfort or in order to provide some easiness, the electronic devices, the traditional electronic devices, they are rigid in nature. They feels uncomfortable for continuous wearing and all. So flexible and stretchable electronics address this limitation, and advanced materials such as graphene, then conductive polymers, carbon nanotubes, etc. These materials allow electric circuits to bend, stretch, twist, and change the shape of the human body without losing the functionality. The flexible electronics improve user comfort, durability, and device reliability. They are widely used in electronic skin, wearable sensors, smart clothing, and biomedical patches, etc. Then moving on to next section, energy storage. We have already discussed about various methods for generating energy, but we have to store that energy. After generating that particular energy, we have to store it into a particular storing unit. That means batteries. So we are having different types of storage technologies. Usually, the energy harvesting sources often provide variable and intermittent power. So it will not produce regularly or constant power from different sources. So therefore, efficient energy storage systems that are essential to ensure continuous operation. So common storage technologies include rechargeable batteries like thin film batteries, supercapacitors, and hybrid energy storage systems, etc. These rechargeable batteries provide high energy density while supercapacitors offer rapid charging and capabilities. Hybrid storage systems combine the advantages of both the technologies. The stored energy can be used whenever harvested energy is unavailable, ensuring reliable operation of healthcare monitoring devices. So the energy storage is between energy harvesting and the device functionality. So the figure shown in the image is the design and manufacturing of high performance micro batteries. So two methods that are one is the etching method and second one is printing technology. In etching method, we are using photolithography. It is somewhat cost-effective method. Then laser engraving method, it is a direct writing or high efficiency method, and plasma etching. And in the case of printing technology, we can screen print or inkjet print or 3D print the circuit or the battery technology or battery layers. We can develop through printing. This is somewhat cheap and fast uh, technology that can be used in battery or storage uh, devices. Another one, we are having the supercapacitor. And in the case of a traditional capacitor, it shows electrostatically between two metal plates. They are separated by a dry dielectric material. But in the case of supercapacitor, you can see in the figure itself, we are having two electrodes, and these electrodes, they are porous activated carbon electrodes are there. Porous activated carbon electrodes means, as we have seen, means we have discussed earlier, the surface area is increased so that these electrodes that are submerged in the electrolyte, this act as a supercapacitor. So in the real world, we are having Maxwell Technologies industrial EPS. It uses capacitors to provide backup, and it can provide huge amount of energy for a short duration of time. Then in the case of supercapacitors, we can have different configurations or types, mainly three. First one is electric double layer capacitors, EDLC, where it's most common type utilizing carbon-based materials with extremely high surface area, such as activated carbon, carbon nanotubes, etc. EDLCs store charge purely through electrostatic means. Next one is pseudo capacitors, where capacitors use fast surface chemical reactions to increase the capacity. So we are combining these two hybrid supercapacitors. It's a combination of EDLC and pseudo capacitor technologies designed to achieve a balance between energy density and power density. Then we are having different power management circuits. We have generated some amount of power from different sources, and we are storing that power with the help of some batteries technology and all. And now we have to manage that particular power. We are using different voltage regulation techniques, then MPPT, then energy scheduling, load management, etc. So we can go through some of the techniques that are used for power management. So wearable devices operate with extremely small batteries, typically 40 to 300 milliamps. So the applications include we are aware with the smartwatches, fitness, etc. So the key challenges is maximizing battery life while maintaining the functionality. The sensors, wireless communication, displays, and processors continuously consume energy. These are the key challenges. The design goal is provide maximum functionality with minimum power consumption. So the challenges in this case are low operating voltage. That means many sensors operate at a voltage below 0.8 volt. The battery voltage must be efficiently converted. Then the ultra low IQ, quiescent current. That means the power consumed during the standby must be minimized. We are all means aware that in the standby mode, the display of the watches and the display of some wearable sensors and all, it will be just cut off that particular time. They're essential for always on monitoring applications. Some applications are always on mode. It consumes more energy. So if we are not the reading is not necessary, the display will be automatically. Okay, means we are some examples like smartwatches and all. We are looking or we are seeing that particular display only there. It will be showing the particular light and all. Otherwise, it will just goes off. Then some small battery capacity issues. Smartwatches may use batteries around 40 mAh. Then limited energy storage demands. Then bursty loads like the sensors wake periodically, means Bluetooth, some other functionalities, and sensors for temperature sensor like heartbeat sensor. They wake up periodically to take the measurements and return to sleep. The power management must handle rapid current variations, etc., efficiently. So, for the architecture of a wearable power management system, uh, the main components will be the microcontroller. It will be a microcontroller, sensors, different types of sensors. There will be a display and Bluetooth low energy, means transmitter and a haptic feedback monitor. That means we are having multiple voltage requirements. That is, different subsystems require different voltages. So for a power management system, it needs multiple voltage levels. So one of the architectures, and it is single inductor multiple output architecture, SIMO architecture, and it projects that deliver multiple regulated voltages from a single power management device. So it tries to produce multiple levels of regulated voltages from a single power management. So it uses fewer inductors, reduced area, then lower power loss, improved efficiency, extended battery life, etc. We can expect these things from the power, power managing unit or power management device. So in order to preserve the battery life, we have to design ultra low power design strategy. That means efficient voltage regulators should be there. We have to maintain for efficiency of the voltage regulator should be maintained, reduce the active power consumption, then leakage current, low leakage current, prevent battery drain during storage and standby. Then the sleep wake operations. It should be optimized that sensors remain sleep in while idle and wake only for measurements, and intelligent power management. That means dynamic power allocation based on workload. Then different type technologies that lithium ion battery technology, coin cell batteries, batteries, silver oxide batteries, different types of battery technologies. These are the where we can improve or where we can have a better architectures or better technologies can be used. Then moving on to self-powered buses. Self-powered means the biosensors usually we are trying to develop is self-powered that it's powering itself, that we are having ECG monitoring systems, heart rate monitoring systems, some blood pressure monitoring systems, similarly glucose monitoring systems. The process begins with an energy harvester which captures energy from sources such as human body parameters like body heat and etc. The harvested energy is then stored in an storage unit such as a battery or supercapacitor. Then the biomedical sensors collect physiological information including heart rate, ECG temperature, etc. The processor or AI module analyzes the collected data, and the IoT communication module transmits the processed information to the smartphone or cloud platforms. This architecture enables continuous monitoring without frequent battery change. So this the system can be we can consider it as a self-powered wearable system. So moving on to some AI area, AI for energy optimization, we can have um, predictive energy management. We can usage of energy or consumption of energy and the nature of sensors, operations, and all, and the adaptive sampling methods and the intelligence, as we already discussed, the intelligent sleep modes and the resource allocation. And depends on the availability of the battery or the power consumption rate, we can allocate the resource accordingly with the help of a AI-based energy optimization model. So then moving on to edge AI, some of many of the technologies means advanced technologies are referring to edge AI. Edge AI refers to the deployment of artificial intelligence algorithms and machine learning models. That means AI ML models directly on local devices such as sensors of smartphones and IoT hardware. Means we are implementing or deploying that AI ML algorithms within the smartwatch or smart systems itself, and rather than relying entirely on the remote cloud servers. So we are relying on we are not relying on the remote cloud servers, but purely relying on the means devices, smartphones, hardware, etc. So we have discussed the variable architectures and edge, and now we will be moving on to the next section, which focuses on the AI-based energy management, IoT-enabled healthcare system, cloud computing, remote servers, and the complete edge cloud server framework. So in the case of edge AI in wearables, we are dealing with edge AI architecture, and we are considering remote servers and a cloud and edge, where the left side it represents the data center, That means it trained models sends the trained AI model to the cloud, and the cloud receives trained models from the remote servers. Remote servers deploy models to the edge. That means sends AI models to the nearby devices. Then wearable and smartphone are edge devices where analyze streaming data. That means continuous real-time processing. So this shows edge AI architecture. So edge AI in wearables. So in wearable devices, the edge AI provide a real-time processing, reduced latency, improved privacy, and lower energy consumption. So these are the advantages of edge AI in wearables. So all the processing and data analysis, majority of the data processing can be done AI with the help of AI within the smart device itself or the wearable itself. Now, moving on to smart healthcare systems. So we are into a era where the healthcare systems are getting means AI based, and remote diagnosis is possible. AI based diagnosis is possible. Remote patient monitoring is possible with the help of healthcare devices or wearable sensors, then wearable healthcare devices. These are all means highly means we are having different types of means we are familiar with different types of wearable healthcare devices. Then analysis of medical images. These are also another area where the medical images are analyzed, and different parameters or different this thing can be data can be taken out from the medical image analyzing techniques. Then the smart hospital system. These are developing means currently smart systems where the patient when the patient is entering into that particular hospital or a clinic, automatically the various parameters like temperature, etc., temperature, pressure, and vital parameters will be collected automatically in the case of smart healthcare devices or smart hospital systems. So this one shows a wearable healthcare device. We have already seen this thing. It is a heart rate and respiratory rate measuring device. Heart rate measuring device where the particular human or the source of that particular sensor is heart rate sensor or some other sensors that are kept in the human body. And these signals are transmitted to various wireless. These information are transmitted through cell phone network to the internet. And this data can be used for various smart hospital systems or remote monitoring systems. And there is a feedback system or intervention system where the user can give feedbacks to the sensors or drug delivery systems and all. These are also possible, but these are also in the developing stage. There are a lot of research areas or developments are going on in this area, and so many domains, so many problems are there. There are means, I will be discussing some of the problems that are means that recent research themes in the coming slides. So the main challenges we are facing is low power density, then device reliability, user comfort, manufacturing costs. These are some of the challenges with these wearable devices, wearable sensors, etc. Then some other issue, some major issue, we can say the security and privacy of the data. So we are using different techniques, data encryption techniques for encrypting data so that the information cannot be leaked to some unauthorized persons and all. So this is one major issue, data security. We are using data encryption techniques, then secure communication methodologies. Then we are using authentication techniques for data security and preserving the privacy. And some regulatory complaints are there. So each countries or each nationalities have own regulatory measures, and also we have to adhere to that norms and regulations. Then it's a it's a future directions where it's a self-sustaining wearables. One means that we have discussed it's the future. Sustaining wearables that they can sustain itself. That means the generator from the body itself, and it can work with the help of that power, and it can sense various parameters and transmit these parameters to the different locations through wireless, and it can analyze the data. So such type of devices or self-sustaining wearables is one of the future means trend. Then evolution of a smart hospitals that we have already discussed. Then digital healthcare ecosystem. It's a part of a smart hospital system and AI-driven personalized medical systems. These are the future direction. Means in near future we'll be having these facilities. Means these are all already in some of the store premium hospitals or environments. These are all available, but it's not that much available for the common people soon in coming out 5 to 10 years. In a period of 5 to 10 years, these facilities or these type of wearable smart hospitals and digital systems, ecosystems will be available to our community or in our India, like countries also. Then one of the major areas where we have to improve or we have to do research is the environmental impact of these devices. That means we are using a lot of energy sources. That battery or energy source is to be eliminated or removed after the usage. So reduced battery waste. We have to reduce the amount of battery that we are using, and low carbon footprint, then sustainable electronics and green solutions. Means the figure shows a lead battery recycling and sustainability model, where means we are manufacturing these batteries and we are using that batteries in some wearables, and after the usage we have to collect these batteries, or we have to collect these materials and we have to recycle these materials, so that it means the systems or energy can be utilized. It's not purely on the micro batteries and all. Means every healthcare system or a healthcare monitoring system, it needs energy and it stores energy in small and large types of batteries. So every types of battery or energy, every type of energy storage system is to be properly maintained and properly recycled and properly used, so that that particular process or that particular loop can be perfectly perfectly done, efficiently done, so that we can reduce the battery waste, we can lower the carbon footprint, and we can move towards the sustainable electronics and green healthcare solutions in for our in the coming generations. So, moving on to recent research trends, we are having means we have already discussed these terms, so nano generators, different types of nano generators, PNGs and TNGs, we already discussed, and some research areas and flexible batteries. We are having different of batteries that are using that are flexible in manner. So they are generating flexible batteries that's having long battery life and higher efficiency. Then hybrid harvesting systems. We are using different types of harvesting systems where energy is harvested from various sources. and AI-assisted management. That means energy can be managed with the help of AI-based managing technologies. But in the case of AI-based energy manager, devices become more complex, and efficient energy management becomes increasingly important in the case of wearable devices. The AI can help optimize the energy consumption by learning how means the user behavior and the device usage patterns. That means the AI algorithms can predict the periods of high and low activity. Means in mobile phones and laptops, we are having, if we are not using the particular device, then the display turns off and the service like Bluetooth, Wi-Fi, etc., will turn off or reduce the consumption of battery. Like that, mobile phones and electronic devices um, are controlling, managing the battery. Similarly, in the case of we are using AI algorithms that can predict the usage and high and low activity and adjust the sensor sampling rates, etc., so that the consumption of battery can be reduced when that we are not using. Some real life examples, we are using some earphones neck bands that can be closed while we are not using or not receiving some calls and all, and we can keep the earbuds into the particular um, holders so that it will not lose battery, or it will not search for Bluetooth devices when they are in that particular mode. Similarly, these sensors can be uh, turned into an idle and off mode to reduce the consumption of battery. Similarly, AI can determine the most time to transmit data or activate specific sensors, and this intelligent energy management significantly extends device operating time and improves the overall system efficiency. So, we are all familiar with the smartwatches. This is not something we are all using, and it is commercially available for us. And we are having smartwatches that can monitor heart rate, oxygen measurement, then sleep tracking, activity recognition, etc. But in the case of IoT, which refers to a network interconnected device that can collect, exchange, and analyze data. That means in healthcare, this IoT enables wearable devices, sensors, and smartphones, and these healthcare providers to communicate seamlessly. That means a wearable sensor continuously collects patient's data. Means the smartwatch is means it's a simple example where it continuously collects data through the wireless communication technologies such as Bluetooth, Wi-Fi. The data can be stored and analyzed remotely by doctors or through our mobile phones. So the IoT improves the healthcare accessibility. So we are having these types of sensors within our smartwatch itself. So it can continuously we are so much aware the means can continuously monitoring and supports data-driven medical decision making, etc. Similarly, these wearable devices are available for us to have the continuous monitoring operations or applications. Mm. Next one is some electronic skin. This shows the electronic skin where it's purely visible. It's not integrated into the skin. It's visible where the flexible sensor networks is placed here, where different parameters like pressure, temperature, etc., can be measured, and it can be termed as a human machine interface. That means here, in the case of remote patient monitoring, that means in one, we are having wearable healthcare technology electronic skin, etc. We can wear that particular skin or particular uh, device. We can say it as a device, but it's so thin and it is ultra lightweight. And this the patients need not to visit the hospital frequency for this health assessment and all. With remote monitoring system, health data can be collected continuously from home and transmitted to healthcare providers. So the heart rate, blood pressure, such vital parameters, the doctors can view these patient data remotely and receive alerts with the help of similar um, uh, devices. And these data or informations, they are integrating it with the cloud technologies where cloud computing provides powerful computation and storage resources for healthcare applications. That means wearable devices generate large volumes of data. Like this wearable device, these sensors can collect a huge amount of data, and the data are collected periodically in each every second or every minute. They are collecting data. The amount or volume of data is huge. So this data is to be stored. The cloud serves as a centralized platform where this data can be stored and processed and analyzed. Then cloud-based systems support advanced analytics, machine learning model training, and popular healthcare studies and long-term patient monitoring. Then this healthcare professional can access this data through the cloud environment. Then the remote servers present in infrastructure used by hospital, healthcare organizations, and these servers store electronic health records, medical imaging data, etc. They also support clinical decisions making systems and telemedicine platforms. Like general purpose cloud services, healthcare servers are designed to comply with strict reliability and security requirements. So the amount of data collected is very large, and the larger data is to be stored in cloud, and means the analysis can be within the sensor or within the integrated device itself. Otherwise, it can be uh, conducted in the cloud. So another case study, another one is wearable sensors. Wearable sensor, you can see the structure of that particular sensor. So this was an invention, and already means this is existing one for people who are having hypertension and certain other conditions. Eating too much of salt means here we are sensing the amount of salt consumed by a particular person. Means here the blood pressure and means other parameters, heart complication to be within control or within limits. So we have to monitor the amount of salt that is taken by the. So the researchers have developed a flexible and stretchable wireless sensing system that is designed to be comfortably worn in the mouth to measure the amount of sodium a person consumes. That this device can be worn as a clip onto the top section of the mouth. And based on an ultra thin breathable elastomeric membrane, the sensors integrates with a miniaturized flexible electronic system that uses Bluetooth technology to wireless report the sodium consumption. So somewhat it's somewhat a big one. Means we can use it as a clip, and it can be integrated into our upper jaw or upper region of our mouth. So now means it's like a dental implant or a dental retainer. Now means the researchers are going on to reduce the size of this thing, and it like the size of a tooth, so that it means different parameters like the consumption of sugar, consumption of sodium, consumption of different minerals, and a sense with the help of this type of uh, sensors that can be placed in our means mouth or means on our can be implanted on our tooth, etc. So this is one of the means developed systems, and the research are going on in this area. Then next one is finger trip wearable microgrid for metabolic monitoring. So it's a powered fingertip wearable microgrid where energy harvesting is done, energy storage is done, and biosensing and metabolic monitoring is done. Means the key features of the system are it harvests energy from finger motion. That means this is, as the name says, it's a fingertip wearable microgrid. Means it is worn at the fingertip and it harvests energy from finger motion, and it monitors metabolic biomarkers and autonomous energy management. Means it is somewhat here we can see the structure of that particular sensor. So the sensor is worn at the tip of the finger, and we are having some fuel cells at the means lower portion of that finger. When the finger moves, it generates electricity or means some potential. This potential is used for means has power source to the sensors, and these sensors take means values or sensors values from the fingertip. So it acts as a self-powering device, uh, and it can transmit data to cloud with the help of um, the self-powering unit and the sensing unit. So it's a silver chloride zinc batteries. We are using a silver chloride zinc batteries. It's the source of this figure. It's a paper, and the research is going on to miniaturize the size of miniaturize the sensor and energy harvesting unit so that it can be so small or small means it can be made into small in size and um, um, it can be worn easily like that. Miniaturization is the main area where it is one of the main area where researches are going on. We are trying to miniaturize different sensors, energy harvesting modalities or models, etc. So some other here in this case, it's a paper in Natural Electronics in 2024, published in 2024. Next one, it is a Springer paper. The research is published in 2025. It's energy harvesting techniques for self-sustainable wearables in remote environments. So for remote environments, they are developing this thing. Means also the wearable system harvesting energy from walking, movement, daily activities like means you're using photovoltaic cells, piezoelectric materials, energy sources, etc. Hybrid powering system or hybrid harvesting system we are using, and simultaneously sensing energy harvesting and self-powered motion monitoring moves towards the battery-free wearable healthcare system. This is paper published in 2025 in spring. Next one, instantaneous wireless self-powered tongue sensor. We have already seen the tongue. TENGs, means electric nano generators. I have already told, means it's one of the major research area in 2024. The paper is published. Means they developed a triboelectric nano generator based wireless sensing platform. The key features are means uses human body as a communication channel and enables wireless transmission up to 8 meter and no batteries required. And the significance is that suitable for wearable health monitoring and smart textiles. This one is paper is a research area in 2024. Some advanced papers are also means under it's not under review. It's not published. Then some research highlights ultra flexible energy harvesting solar system. And this one is the published in Nature Communication in 2024. Here the researchers developed a ultra flexible system that combines energy harvesting and energy storage. Means here it's a simple thing. As you can say, it's a energy harvesting and energy storage system in a single device. But we have to do a lot of research and lot of work is to be done the system and integrating that two units into a single device. The system can collect energy from environment, store it, and provide a stable power supply for the wearable electronics. And the flexible design makes it suitable for next generation healthcare wearables. The main advantage is continuous operation even when harvested energy is not always available. So energy harvesting is happening and energy storage is also happening. So if the harvested energy is not available, we can go for the stored energy. Okay. Then another one, this ambient energy harvesting technologies for wearables. That's one paper. It is Nanobiotechnology, Journal of Nanobiotechnology, published in 2024. It combines various different types of energy harvesting, ambient energy harvesting. This study reviewed different energy harvesting methods like for wearable devices, including solar, thermal, piezoelectric, etc. Then the researchers looked at how these technologies can be combined. As I have already discussed about hybrid energy generators. So the researchers discussed how these technologies can be combined to create self-powered wearables. The work provides a roadmap to the development of sustainable healthcare devices with reduced battery dependency. So this is another area where we are developing uh, energy or hybrid energy sources from different energy sources. We are combining these energy sources into a hybrid source that provide power without any lag. Then another one, it is human motion energy harvesting nano generator. So this is also a sensor paper in 2024. The researchers developed nano generators that convert human motion into electrical energy. That means activities such as walking, running. These are all the basic activities. Walking, running means I have mentioned walking, running, body movements. So many slides I have mentioned these walking, running, and the body movements. These are all the means activities where a human body can collect uh, uh, energy or for generating power. This study demonstrates self-powered smart systems that can perform sensing and energy generation simultaneously, reducing the need for external batteries. And one of the recent one is a research in texting in 2025. The research paper based on textile-based triboelectric nano generators. We have already discussed the triboelectric nano generators. And in the case of triboelectric nano generator, there is a gel electrode based triboelectric fiber, and it can be incorporated to our textiles or our dress materials or wearables. And with the help of various friction type movements, or means actually the triboelectric nano generators are friction based electric nano generators. So friction type movements from the skin on the particular textile or fabric, it will energy, and this energy can be for this thing uh, sensor integration, so powering the sensors. The research integrates textile fabrics to energy, then to generate clothing, energy from clothing, and the body parts movements. The smart garment, we can have smart garments that are capable of energy harvesting and self-powering. We can develop self-powering devices from these textiles. These are all the areas where we can have, or we can find some have some literature and take some problems so that we can have some research on that area. And means there are so many agencies they are support our research works